Okay, now we're going to look at energetics. Energetics, part 3. All right, Hess's law. Hess's law basically says you can just add equations together to get the overall equation. Cross things off as need be, multiply as need be. All right. An example, if we look at, and what this does is it really takes advantage of enthalpy being a state function, meaning it doesn't matter the path that we take to get there. You just look at the enthalpy of the products and reactants. So say I've had, I can have A making B, straightforward, or I can do a series of reactions, A to C and then C to B. The change in enthalpy of X is going to be equal to the change in enthalpy of Y plus the change in enthalpy of Z. The only thing that I would caution you in applying Hess's law is to make sure that the signs are appropriate. I think that the IB tries to trick you sometimes in knowing how to add them and what the signs should be. Alright, there is and they don't always use a graphical representation that I find easy to understand. And they call this an energy cycle. CO2 gas. So I have carbon reacting with hydrogen in a heat of formation to make methane gas. I could also look at the combustion reaction for carbon and hydrogen, and these would basically be your heats of combustion that are in a table in your data booklet. Right. And I could use these in the same type of Hess's law by looking up the equation to get the heat of combustion of methane. Right, so using the heat of formation of methane and the heats of combustion for carbon and hydrogen, I can get the delta H of combustion for methane. I hope that's somewhat clear. All right, let's move on to bond enthalpies. Okay, and this is the energy change when 1 mole of a covalent bond is broken. Oh, and I need to say covalent bond in the gaseous phase is broken into its gaseous atoms. Okay, if you notice, everything is in the gas phase. So if I have the covalent bond between X and Y in the gas phase going to form X in the gas phase and Y in the gas phase, that would be the definition of bond enthalpy. Remember, these are all going to be endothermic because it always requires energy to break a bond. Okay. Interesting, for diatomic elements, these bond enthalpies are known precisely. Okay. For other bond enthalpies, they do a series of experiments and determine the average from different molecules containing that bond. Okay, so there is some error introduced when using those bond enthalpies. one, if everything's not in the gas phase, there would be more error, and two, because your empirical data that's used from the tables is based on average from different molecules. Okay. So we can use those bond enthalpies, though, in calculating the enthalpy of a reaction. And remember, this can change depending on whether you're talking about a specific reaction like combustion or neutralization, but those are all just changes in enthalpy. It's for a reaction. Sometimes they just are specific as to what reaction it means. But the delta H of the reaction, if we use bond enthalpy, is going to be the change in enthalpy of the bonds broken minus the change in enthalpy of the bonds formed. It is most useful to draw Lewis structures and count the number and types of bonds. Okay, this is more in a bookkeeping kind of thing. Remember that the heat, and then we have heats of formation and heats of combustion. Okay. Heat of formation of an element in its normal state is 0. Okay, and please remember that is in its elemental state. So for things like oxygen, it would be O2 in the gas phase. Its enthalpy is taken to be 0. Right. So another way to look at the enthalpy change of a reaction is to take the N times the heats of formation for the products minus N times, oops, sorry, sum is supposed to be in the front, delta H of the reactants. Okay, if you are using the combustion, you would have the sum of the delta H of combustion for the reactants minus the sum of N delta H of combustion for the products. Those are different. Delta H vaporization might be another thing. The enthalpy change for the change of state from a liquid to a gas, this will be endothermic. You can use the same one for gas to liquid, but make sure that you make it exothermic. Same with heats of fusion. Going from a solid to a liquid will be endothermic because it's going to a higher energy state. From a liquid to a solid will be an exothermic state. Make sure that you pay attention to the signs. All right, entropy and free energy. Remember that entropy is the measure of the disorder. That says disorder. Its symbol is S. Delta S at standard conditions is positive for an increase in disorder. Delta H in the standard state is negative for a decrease in disorder. Or becoming more ordered. Free energy is G, and G will be negative for a spontaneous process. And remember G, looking at an equation, delta G is equal to delta H minus T delta S at standard state. Okay. If I have an exothermic process that also increases in disorder, this will always be spontaneous. If I have an endothermic process with a decrease in order, this will always be unspontaneous. Is that a word? Or maybe we can just say never spontaneous. How about that? Okay, because this will always be negative, this will always be positive. Okay, if I have an exothermic process that is becoming more ordered, this will be spontaneous at low temperatures. If I have an endothermic process and it is becoming more disordered, then this will be spontaneous at high temperatures. Okay. At equilibrium, delta G is equal to 0. For a phase change, you can use that to determine the melting point or the boiling point, because those are equilibrium. Your delta G would be 0, and you can set delta H over delta S equal to T of your melting point or boiling point. And that actually ends the review for energetics. We should be doing a number of problems within the class.